In this presentation, I am going to explain the gate questions and answers for the year 2023, and the topic covered is analog electronics. Now let us see the first question of 2023 gate question, that is, consider the op-amp based circuit shown in the figure. This is the op-amp based circuit. Ignore the conduction drops of the diodes D1 and D2. D1 and D2, the drops are conduction drops are ignored. All the components are ideal, and breakdown voltage of the zener is 5 volts. The breakdown voltage of the zener is 5 volt, Vz equal to 5 volts. And which of the following statement is true? Which of the, that is, there are 4 options are there. And here the input voltage applied is equal to 10 sine 1000 t. That is the input voltage applied here. That is applied to the inverting terminal of the op-amp through a resistor, and this feedback resistor is the, and this is the diode D1 and D2, and of course this is the zener diode, and output is taken at this point. Now the options are A, the maximum and minimum values of the output voltage V0 are plus 15 volt and minus 10 volt respectively. Second option B, the maximum and minimum values of the output voltage V0 are plus 5 and minus 15 volts respectively. And the option C, the maximum and minimum values of the output voltages are V0 are plus 10 volts and minus 5 volt respectively. The option D, the maximum and minimum values of the output voltage V0 are plus 5 volt and minus 10 volt respectively. And we will be analyzing the circuit in the coming slides, and the answer is option D. And in this case, the op-amp biasing voltage is, these are the biasing voltage given, plus 15 and minus 15, and will be, or it will be explained in the coming slides. Now continuing the 2023 gate question, that is same problem as such here. This is the circuit that is considered, and the input voltage equal to 10 sine 1000 t, and here the input resistance that is connected to a inverting terminal of the op-amp, and non-inverting is grounded, and this is the feedback resistance, and in that series there's a diode D1, and in this one another D2, and the zener diode is the output is taken here, and these are the biasing voltage plus 15 and minus 15. Now during the positive half cycle of the input, during the positive, that is input, you can see that one, this is forward bias, D1 is forward bias, as well as the zener diode, that is DZ out forward bias. Same time, this diode D2 is a reverse bias. Now the corresponding equivalent circuit during the positive half cycle, the equivalent circuit is this one. The input voltage, which is equal to 10 sine 1000 t, and the input resistance R. And here, since the diode D1 is forward bias, we can consider it is a short circuit because we are neglecting the diode drop. Therefore, that is short circuit. And since this is also forward bias, zener is forward bias, it is shorted, and the diode D2 is reverse bias, that is open circuited. Therefore, this is the equivalent circuit during the positive half cycle of the input. Now, if you see this one, we can see that it is an inverting amplifier configuration. Input is given at the inverting terminal through a resistance R, and here the feedback resistance equal to R, and this is the output voltage. And now for inverting amplifier, when the input voltage reaches to maximum input voltage reaches to 10 volt, then output voltage is given by minus feedback resistance divided by the input resistance into the input voltage. Therefore, it is equal to minus RF divided by R1 into 10 volt, or which is equal to minus of 1 kilo ohm divided by 1 kilo ohm into 10 volts, or that is equal to minus 10 volts. That is, during the positive half cycle of the input, when input voltage reaches to maximum 10 volt, the output voltage is equal to minus 10 volt. Now during the negative half cycle, of the input, that is actually it is from pi to 2 pi radians. During the negative half cycle, we can see that one, this is reverse biased, D1 is reverse biased, and similarly here this is forward bias, diode is forward bias, D2 is forward bias. But since the input voltage here, if if it is crosses the maximum Zener voltage, then this will the voltage across the, this one will become the Zener breakdown voltage will be here. Therefore, that is the Zener breakdown voltage comes here. Of course, this is forward bias, that is shorted, and since this is reverse bias, it is open circuited, and therefore this is the equivalent circuit of this one during the negative half cycle of the input. And in that case, we can see that one, the output voltage here, it is equal to this voltage, whatever the Zener breakdown voltage, that is equal to 5 volts with a plus here, minus here, therefore plus 5 volt. Therefore, the output voltage equal to plus 5 volt. The maximum output voltage equal to plus 5 volt during the negative half cycle of the input. Therefore, the maximum output voltage plus 5 volt, and the minimum output voltage is equal to minus 10 volt. Therefore, the maximum and the minimum values of the output voltage are, which is equal to plus, that is the maximum plus 5 volt and minimum minus 10 volts respectively. Therefore, the answer is option D. You can see that one here. The answer is option D. The maximum and minimum values of the output voltage are plus 5 volt and minus 10 volt. Now let us see the second problem of 2023 gate question. That is second, an 8-bit ADC converter or that converts analog voltage in the range of 0 to 5 volt to the corresponding digital codes per the conversion as per the conversion characteristic shown in the figure. This is the conversion characteristic shown here. And for V in voltage 1.9922 volt, which of the following digital output given is in hex is true? The options are option A 64H, B 65H, option C 66H, and option D equal to 67H, corresponding to this voltage 1.992 volts. What is the corresponding hexadecimal number? Or that is, we have to see 1.9922 volt is that. Therefore, in this case, ADC maximum voltage is 5 volts, that is 5 volts, and it is an 8-bit ADC. Therefore, the step size is that, which is equal to 5 volt divided by 2 to the power of n minus 1, which is equal to 5 divided by 2 to the power of 8 minus 1, or 5 divided by 255. This is the step size of the analog to digital converter. And for an input voltage of 1.9922 volt, what is the corresponding digital output? Therefore, it is equal to 1.9922 volt divided by the step size, that is 5 divided by 255, which is equal to, we can say that one, it is equal to 101.62 in decimal, and it is approximated to 102 in decimal. Now, then hexadecimal corresponding to 102, which is equal to 66, meaning that it is equal to 6 into 16 to the power of 0 plus 6 into 16 to the power of 1. Therefore, 66H, that is the answer corresponding to a input voltage of 1.9922 volt. Therefore, the answer is option C, 66H. Now let us see another third problem of 2023 gate question. That is third one. The Zener diode in the circuit has a breakdown voltage of 5 volt. This is the circuit. In this, Zener diode has a breakdown voltage of 5 volt. The current gain beta of the transistor, this one current gain is of the beta in active region, it is 99. That is beta equal to 99. Ignore the base emitter voltage drop. That is VB, that drop is neglected. And the current through the 20 ohm resistor in milliamperes. What is the current through the 20 ohm resistor? That is in milliamperes. That is be rounded off 2 decimal places. Now coming to the circuit here, let us consider that when Zener is off, that is, it is open circuited. When Zener is off, apply the Kirchhoff's voltage law to this loop. That is, KVL is applied to this loop when Zener is off. And then 25 volt is the potential rise, a 25 minus drop across 7k ohm resistance. Because here it is broken, it's off, therefore IB is same as this current. For IB into 7 kilo ohms, then this drop is neglected, and this drop equal to 10 ohm into IE, that is IE into 10 ohm plus IE into 20 ohm. IE into 10 ohm plus 20, which is equal to 0. That is, we are applying the Kirchhoff's voltage law to this loop. And 25 minus IB into 7 kilo ohm minus, that is IE equal to, the emitter current is equal to beta times IB, that is IC plus IB, beta times IB plus IB, or 1 plus beta times IB. For 1 plus beta times IB, that is IE, into the 30 ohms equal to 0. Beta is given as 99. Substituting that one here, 25 minus IB into 7 kilo ohm minus 1 plus 99 into IB into 30 ohm, that is equal to 0. And then we can solve what is the base current. Base current is given by 25 divided by 7000 plus 3000, which is equal to, and the answer is 2.5 milliampere. So for the base current in this loop, it is equal to 2 milliampere when this is not conducting, or that is off. And in that case, the emitter current can be calculated, which is equal to 1 plus beta times IB, or 100 into 2.5 into 10 raised to minus 3, which is equal to 250 milliamperes. Therefore, the current through the 10 ohm resistance, since this is off, the current through 10 ohm resistance is same as the current through the 20 ohm resistance. Therefore, we have to, one thing to be proved is that the drop across 10 ohm resistance, when this current is flowing, 250 ohm milliampere is flowing through the 10 ohm resistance, the drop across that one is given by 250 milliampere, 250 into 10 raised to minus 3 into 10 ohm, and that we can get, it is equal to 2.5 volt, and the Zener breakdown voltage equal to 5 volt. Therefore, since this voltage is less than the Zener breakdown voltage Vz, this is not, this is not coming to the breakdown region. Therefore, this is open circuited. Just to verify that, this is actually Zener is not in breakdown, and the assumption is what we assumed is correct. Therefore, under this condition, this is open circuited, and the current through the 20 ohm resistance is same as the current through the 10 ohm resistance, which is equal to IE, that is equal to 250 milliamperes. Therefore, hence the current through the 20 ohm resistor, which is same as the emitter current IE, which is equal to 250 milliampere. Therefore, the current through 20 ohm resistor in milliampere, that is equal to 250.